Command optimum in the overlapping generations model from my book Public Economics, Chapter 3.3. Hello there, and thanks for looking into this video, which is the third video in a row on overlapping generations models. In the first two videos, we have looked at the decentralized economy. Now we look at the command optimum, where a central planner is maximizing social welfare, which consists of the lifetime utility of this and future generations. Now in Chapter 2 on the Ramsey model, the neoclassical growth model, we learned that with the help of the solution for the central planner, we can derive the allocation of a Pareto efficient allocation. And when we compare it to the decentralized economy, under certain conditions, the two allocations are equal. So this equivalence results holds when in the decentralized economy we have perfect competition in goods and factor markets and constant returns to scale and production. And then the two allocations were equal, and the allocation in the decentralized economy was Pareto efficient. Now we wonder if these kind of questions or these kind of results also hold in the overlapping generations model, where people have finite lifetime. And we will find that this may not be the case. So we find certain conditions which must hold that the competitive economy is equal to the one of the social planner, the command optimum. And this will be that parents are altruistic and leave bequests to their children. And we may also find that the competitive economy is not Pareto efficient. And so this result contrasts with the one from the neoclassical growth model. And the reason, of course, is that we have finite lifetime. Now let's get into the material. And for this reason, I would like you to download the slides from my chapter 3 on the book. You can find all these slides on my homepage, together with the computer code, with solutions to selected problems, and so on. So please visit my homepage. Now, in Chapter 3 of the overlapping generations model, we looked first at the decentralized competitive economy. Now we look at the command optimum. And let us briefly review how we modeled the overlapping generations population in the competitive economy. This will, of course, be the same in the command optimum. So we have a household that lives for 2 periods. So we have workers and retirees. So in the first period, households supply labor inelastically 1 unit. So they work 1 unit, let's say, which is equal to 40 hours a week. And when they retire, they do not work. So we identify here time periods with a period of, let's say, 40 years. So the first 40 years we work, and the last 40 years we retire. And these 2 periods need to be of equal length. Production takes place with uses capital and labor, and we assume constant returns to scale. And population grows at rate n. So the demographics will be the same in the command optimum as in the decentralized economy. So NT is the number of young people in period T. So in period T minus 1, we had NT minus 1 people, and N is the growth rate, the population growth rate. So we have 1 plus N children for each person in the economy. And the population growth rate N is the same for the number of young people N and for total population. We assume that households consume C1T at young age when they are age 1 in period T, and C2T plus 1 in period T plus 1 when they have age 2. So the super index 1 or 2 is the age, 1 for workers, 2 for retirees, and the subindex T or T plus 1 is the time index. And lifetime utility of the household is uppercase U, which is a function of consumption young age and old age. Instantaneous utility is denoted by lowercase u, and future utility at old age is discounted with the factor beta. Now let's skip into the command optimum. Here we have a social planner, and he maximizes the utility of the cohorts presently alive in period t equal to 0, and of the next t minus 1, uppercase t minus 1 generations. So the generations born in period 1, 2, and so on up to period t minus 1, uppercase t minus 1. So here we have beta times u of C2, 0. That's the utility in old age discounted by the factor beta of the present old generation, who are old in period 0. And on the right-hand side here, the second factor, we have the lifetime utility of the generation born in period t. And we have the discount rate R of the central planner. So for example, if he weighs each generation equally, R set equal to 0. The central planner maximizes social welfare function U in equation 23, subject to his resource constraint. The resource constraint is given in equation 24. On the left-hand side, we have the total resources available, the capital stock K, and we assume that it does not depreciate. So the beginning of period capital stock K is also available after production. And the production with the help of capital K and labor N. So this is F of K, N describes total production. N is equal to the number of young people, and since they all work 1 unit, it also describes total aggregate labor supply. Remember that the old people do not work. Now, total production and what's left of the capital stock can be allocated to either the next period capital stock, KT plus 1, or to consumption. And the young people consume NT C1T, and the old people consume NT minus 1 C2T in period T. So we have NT young people in period T and NT minus 1 old people in period T. These are the people who were young in the previous period T minus 1. If we divide it by the number of young people NT, we get equation 25, which is our resource constraint in per capita variables, or to be more exact, in the capital stock per number of young people. So we have expressed the capital stock per capita here as lowercase k in order to consider stationary variables. And when the central planner maximizes social welfare, equation 23, subject to the resource constraint 25 with respect to consumption C1T, C2T, and KT plus 1. So when he's forming more formally his Lagrangian and maximizing with respect to present consumption C1T of the young, next period consumption CT 2T plus 1 of the then old people, and with respect to next period capital stock KT plus 1, we derive the 3 first order conditions 26, which can be condensed into the Euler equation, which is the bottom equation. So what's the intuition for the bottom equation? Well, the central planner can use one of the marginal unit of his resources, extra unit, either to give it to the young who consume today and get marginal utility U prime of C1T, or he can increase the capital stock, next period, KT plus 1. This gives him extra resources 1 plus F prime of KT plus 1 next period, which can be spent on consumption of the old in the next period, C2T plus 1, which can be must be discounted by the factor beta. So because lifetime utility is additively separable for each generation, and future utility or utility at old is discounted. And we also have a first order condition 26b, which becomes 27a, which informs the central planner how we should allocate resources between 2 generations alive, C1 and C2 in a given period t. Now in steady state, our conditions are described by equation 27a and 27b. So in steady state, the consumption of the young is constant, equal to C1, and the consumption of the old is also constant, equal to C2, and the capital stock per young worker is equal to K. Now with the help of equation 27b, we can derive what's called the modified golden rule. So if we multiply the right-hand side, the two factors on the right-hand side, we have 1 plus f prime is equal to 1 plus r plus n plus r times n. And if we subtract 1, we get to the modified golden rule. Which is f prime is equal to r plus n. So that's the modified golden rule for the central planner, and we use the approximation that r times n is approximately equal to 0. So if the population growth rate is small, let's say 1%, and the discount factor is also small, a couple of percentage points, then of course the product r times n is even smaller, so we may neglect it. If the central planner attaches equal weight to each generation, so that r is equal to 0, then the marginal product of capital in the steady state is equal to n. That's the modified golden rule of the OLG model central planner. Now let's see if our allocation is Pareto efficient or what's the efficiency condition. Therefore, we introduce a new variable, C, which is total consumption per young people. So the young one consumes C1 in steady state, and the old one consumes C2. And the old people are fewer, so the number of old to young people is 1 over 1 plus n. So we have to divide C2 by 1 plus n when we divide total consumption by the number of young people, nt. Our resource constraint in steady state simplifies to production minus n times k is equal to consumption c. So we can see this from the resource constraint 25. Here when we set C1t to C1, C2t to C2, then we have total consumption per worker, young worker. And if we set kt equal to kt plus 1 equal to k, then just n times k is left over on the right-hand side, and this is equal to f of k. So equation 25 in steady state becomes equation fk minus nk is equal to c. Now let's see what's happening if we increase the capital stock in steady state, how it affects consumption. So we just have to take the derivative of the second equation with respect to k, and we find that the derivative here, if we take the derivative of the left-hand side with respect to k, it's f prime k minus n. So the marginal product of capital minus n. Now, and we wonder when this is smaller than 0, because in this case we will show that consumption could increase not only in steady state, but also during the transition if we decrease the capital stock. So in particular, I postulate here that if f prime, the marginal product of capital, is smaller than the population growth rate n, everyone can be made of better if the capital stock is decreased. Now let's look what's happening to consumption of the people during the transition. Transition in this particular case, when we reduce the capital stock by amount dk, let's say 1 unit, what's happening is we save 1 unit less for next period, and this is available for consumption, C1t plus 1 plus m times C2t. So if we decrease the capital stock from the steady state capital stock, consumption in the first period will go up. Now in the next period, let's assume we are in the new steady state and we keep the capital stock constant at the new value k minus dk. What we have shown here is that in this case, if decay is smaller than the 0, consumption goes up. So both during the transition in the first period or the one period of transition and in the new steady state where we have reduced the capital stock, consumption of both generations or all generations has increased, and therefore, of course, lifetime utility and welfare has increased. So in order to have Pareto efficiency, we must demand the opposite, that this derivative is larger than 0. And or equally expressed, if f prime of k, if the marginal product of capital is smaller than n, everyone can be made of better if the capital stock is decreased, both in the first period of the transition and in the new steady state, and we have dynamic inefficiency. So let's go back to our command optimum. We have derived that f prime is equal to r plus n. So as long as our weight here, our discount factor r, is equal or larger than 0, then we don't have the case that the economy is dynamically inefficient. Only if the central planner weighs the utility, the lifetime utility of future generations larger than that of the present generation, so if r is smaller than 0, do we have a situation which is dynamically inefficient. Okay, now let's look how this result carries over to the decentralized economy. We have shown in chapters 3.2 in the previous tutorial that the dynamics, the equilibrium of this economy is described by first order difference equation in the capital stock KT, so that the aggregate capital stock next period, 1 plus n times KT plus 1, is equal to the savings ST. And the savings depend on the wage rate WT and the interest rate RT plus 1, which themselves are again functions of the capital stock. In the logarithmic case, so log utility and with Cobb-Douglas production, we have shown that the dynamics are described by the second equation of KT plus 1 as a function of KT, and the steady state stock, capital stock is equal to K, is equal to the expression on the right-hand side of the bottom equation. Now we wonder if for this example here, if this is dynamically efficient or not, this decentralized economy. And of course, the same argument here holds. It depends whether the derivative, the marginal product of capital F prime, is larger or smaller than the population growth rate n. And in the decentralized economy, the interest rate, the real interest rate is shown to be equal to the marginal product of capital F prime. And for our example here, this is equivalent to the condition that the left-hand side here is larger or smaller than the right-hand side. Now let's take some typical values here of modern economy. Let's say Germany, we have a population growth rate which is basically 0, so the right-hand side is 0. We have a production elasticity alpha that's equal to about 0.35, and the discount factor of our households for future utility, well, we usually use something that it's something like 0.96 annually, so that we have a real interest rate of 4%. And you can see that clearly in this case, we have dynamic efficiency. Things are a little different when we have depreciation. So when we introduce depreciation, which we have neglected so far, we have to reduce the marginal product of capital by the rate of depreciation, delta. So we have f prime minus delta is larger or smaller than the population growth rate. And this condition is more likely to be met. So we have to check here in our model if our economy is dynamically efficient. So if the marginal product of capital minus the depreciation rate is less or more than the population growth rate. And of course, this is an important condition that we need to consider. For example, let's look at the policy question that we look at in chapter 6. There we wonder if we should increase or decrease public pensions. Now you will find out that with a pay-as-you-go pension system, if you increase pensions, then the savings will go down and the capital intensity will decrease in our economy. Now, if we are in a dynamically inefficient economy, when we start this consideration here, it means that any reduction in the capital stock will increase dynamic efficiency, and therefore we will find, of course, in this particular case where we have a dynamically inefficient economy, that higher pensions are good. So we have to be careful to interpret our results, or therefore results, for example, when we consider policies that decrease the capital stock. This might always be beneficial in economies which are dynamically inefficient. Now let's go back to the decentralized economy and get back to the second question: when is our decentralized economy equivalent to the central planner's optimum? And we will find that this is the case when we introduce altruism. So if we look at total bequests, some of our bequests are planned because we are altruistic and love our children, but some are accidental because we die prior to what we expect. Or let's see, for example, we get corona and die at age 30 or 40 or 50, and we didn't plan for this. The mean inheritance in the United States in the 80s was around $40,000. In the 90s, it was around $55,000. In modern times, it's around $70,000. So conditional on that you receive an inheritance, it's around $70,000 on average in the United States. About 2%, the annual aggregate inheritance amounts to approximately 2% of gross national product. And intended transfers and bequests, so some of the bequests because of tax reasons are transferred prior to this. So people start to transfer some of their wealth to their children in order to save taxes, or for their children to save inheritance taxes prior to their death. Now, if you also count this number, we find that about 20% of individuals' net worth stems from inheritances. So on the one hand, we have people like Bill Gates who build up all their fortune just because by being entrepreneurs and building up this firm and going to the stock market. But we also have the children and the grandchildren of the Rockefellers and Carnegies who inherit a lot of wealth from their parents or grandparents. Now, in case our individuals, our agents, our households are altruistic, we may express their lifetime utility with the help of the utility function VT, lifetime utility VT. So they still receive utility from consuming C1T and C2T plus 1, and they still discount future utility by the factor beta. But now also the lifetime utility of their children, VT plus 1, enters their happiness, their utility VT, and let's assume that they discount the lifetime utility of their offsprings by the discount rate R. Now, if we lack this lifetime utility T, or rather use the same expression and use it to express VT plus 1. So it's VT plus 1 is equal to UC1T plus 1 plus beta UC2T plus 2 plus 1 over 1 plus R times VT plus 2. And do this and substitute it in equation 29 and do this recursively, we get to the expression VT on slide 46. So there we can show that the lifetime utility of the altruistic parent, of the altruistic person, is just an weighted utility of the consumption of all generations over the next infinite period. So from period I equal to 0 to from period T up to period infinity. So the consumption of the children, grandchildren, and grandchildren, and so on enters our lifetime utility VT. Now this is equivalent to the one of the central planner. Perhaps we may use a different discount rate here, R, but otherwise it's equal. Now let's look at the budget constraint. In the first period we work, get the wage rate WT, and we work 1 unit of labor inelastically. So our labor income is also WT. We receive bequests from our parent bequest T, back T. We spend it on either consumption or savings. In the next periods, our income is equal to savings ST and to interest on savings RT plus 1 times ST. We spend it on consumption CT T plus 1 and leave it to our children so that each child gets the bequest back T plus 1. Since we have 1 plus n children, we have to multiply back the expression back here, the variable back T plus 1 in equation 30b by the factor 1 plus n. We also assume that the bequests are larger or equal to 0, so you cannot leave debt to your children. This is sometimes written in tax law, so if you have an inheritance in some countries in this world, for example Germany, and your parents leave debt to you, you can decline to accept the inheritance. When we substitute ST from equation 30a in equation 30b, we derive the intertemporal budget constraint. So on the right-hand side, we have total income, which are wage income plus bequests in period T. And on the left-hand side, we have our expenditures. So we spend it on consumption today, consumption tomorrow, which we discount by the interest rate, 1 plus RT plus 1, and on bequest to our children, 1 plus n times back T plus 1. Now, when we optimize intertemporal utility VT of the altruistic generation with respect to the budget constraint, we derive the conditions 32a, b, and c, which are our first order conditions with respect to consumption today, C1T, consumption tomorrow, C2T plus 1, and the bequests that we leave back T plus 1. And here we have an inequality constraint, meaning that this equality only holds if bequests T plus 1 are larger than 0. And we can transform this to our two conditions, 31a and 33b. So 33a is our Euler equation, which tells you whether you should consume 1 unit today or save it and consume it tomorrow. And the condition 33b is the optimality conditions on your bequests. And you compare the utility you get from consuming 1 unit today or save it and leave it to your children. Now you observe that these conditions 33a coincide with those of the command optimum if there's an operative bequest motive if bequest T plus 1 is larger than 0. Then these two conditions are identical to those of the central planner. So the decentralized economy, we have shown that this decentralized economy is equivalent to the command economy if both generations are altruistic and if the bequest motive is operative. So that's different from the Ramsey model or the neoclassical growth model, where there is these close one-to-one correspondence. Here in the overlapping generations model, it's not, because lifetime is finite and we only behave like an infinite planner if we have operative bequest motive. And of course, again, the same reasoning applies to this decentralized economy with altruistic bequest. We have dynamic efficiency as long as this discount rate R is not below 0. So is this a realistic assumption that our households are altruistic? Well, Altani, Hayashi, and Kotlikov looked at the implication of altruism and found, when we look at the intergenerational risk-sharing behavior, that empirically we have to reject it. So it's probably safe to assume that, different from the Ramsey model, if we study overlapping generation models, that the command optimum and the decentralized economy, even if we have perfect competition, do not imply the same allocations. Now let me show you what we consider next. In the next video tutorial, you will study the dynamics in the decentralized economy, and you will learn how to solve the dynamics numerically with the help of the software either MATLAB or Gauss, depending on your preferences. And we will study the so-called turnpike behavior. So if you also are interested in the numerical analysis of our command optimum that we studied here in the last 30 hours or the last 30 minutes, last 30 minutes, please also upload the video on the turnpike behavior, and it also introduces you to the MATLAB code or the Gauss code and shows you how to solve nonlinear equations problems with the help of the computer code. So thank you for your attention.